All right, so let's talk about molecular geometry. And the molecular geometry falls under the umbrella of Vsepr theory. Vsepr stands for valence, shell, electron, pair, repulsion. If you're given any molecule, so let me just do this with a few examples. We could look at something like ICl3, ICl4 plus, ICl4 minus. So there's a process that will allow you to arrive at these geometries. I tend to like to use ODEC methodology to consider the electron configurations. I'm going to use ODEC to begin, and then I'm going to show you a shortcut. So for iodine, iodine has a 5s and a 5p. And of course, it has 5 d orbitals that are available for electron promotion. So in the ground state, it's 5s2, 5p5. So you would ordinarily expect 1 bond for iodine, but here it's making 3. So I can do promote an electron, and now I have 1 bond I can make. So a lone arrow means I can make a bond. So here's 1 bond with a chlorine, 2 bonds with a chlorine, 3 bonds with a chlorine. If I start to assemble this together now, iodine has 2 lone pairs, 1, 2, and it's making 3 bonds, 1, 2, 3. Now I'm tipping my hand because I know that this is a T-shaped molecule. So I'm going to explain how I know this geometry in just a moment. Each chlorine is going to have 3 lone pairs. Its ground state electron configuration is going to look just like that of iodine before I promoted electrons. When I have 5 areas of electron density, there is a family called trigonal bipyramidal this fits into. Trigonal bipyramidal with only 3 bonds is a T-shaped molecule. So let's imagine how we figure this out. So when I know that I have 5 areas of density, and I know I have 5 areas of density simply by counting them, I have 1, 2, 3, 4, 5. Draw the central atom. With trigonal bipyramidal, you have 3 of these environments within a plane. And so it's kind of difficult to visualize this. So imagine, if you will, this iodine is straddled such that one of the atoms goes into the plane, 1 jettisons out, and 1 is in the plane. But if I were to twist it, these would all hover in a hypothetical horizontal plane. Then I have 1 that goes straight up. I have 1 that comes straight down. That's trigonal bipyramidal. Now the whole essence of Vsepr is valence shell electron pair repulsion. Lone pairs take up more volume than do bonding pairs. And when lone pairs are 90 degrees from other orbitals, they're especially repulsive. So what you need to understand is that I'm going to label these positions as an A and an A. The A is for axial, and E and E and E. The E is for equatorial. If I have a lone pair in the axial position, this lone pair is 90 degrees to this equatorial position and to this equatorial position and to this equatorial position. If I put the lone pair in the axial, I'll have 3 repulsive interactions. Now let's contrast that to what if I put the lone pair in the equatorial position. If I put it in the equatorial position, I'll have a 90-degree interaction with the axial and with the axial, but not with the other equatorials. So if I put in the lone pair in the equatorial position, I'll have 2 repulsive interactions. The thinking here is very simple. It's better to have 2 repulsive interactions than 3 repulsive interactions. Therefore, the lone pairs must lie in the equatorial positions. So now I'm going to take off these labels. And we're going to replace these labels with, in the case of the equatorial position, 2 of the 3 equatorial positions will have lone pairs. I know iodine has 2 lone pairs. So let's go lone pair, Cl, Cl, Cl. Now I'm not going to put the lone pairs on chlorine. I simply want to emphasize the shape of the molecule. And if you look at this through a trained eye, you have a T. It is T-shaped. All right, let's talk about the shortcut. Find the central atom. In this case, it's iodine. How many valence electrons does iodine have? Of course, we know it has 7. How many atoms are bonded to it? Well, there are 3 Cl's that are bonded to it. 7 plus 3 is 10. There are 2 electrons per bond. That's 5 areas of electron density. This leads you to the trigonal bipyramidal family. That's the shortcut. Now, let's look at the other 2 molecules. Let's look at ICl4 minus. Again, iodine initially has a 5s2 and it has a 5p5. I need to make 4 bonds, but I'm also adding an electron. So let's just go ahead and add the electron. Then let's promote. Of course, this is hybridization. Let's promote the 5py into one of my d orbitals. Now iodine is positioned to make 4 bonds. There are, count them with me, 1, 2, 3, 4, 5, 6 areas of electron density. That's the octahedral family. These are all in the same plane. Then you got one above, you got one below. Same thing with the lone pairs. You want the lone pairs in this case to be axial. And then the 4 chlorines are in the equatorial position. Not going to show the lone pairs. I'm simply going to emphasize the geometry. This geometry is square planar. Finally, let's look at ICl4 plus. Many of the same principles, 5s2, 5p5, only this time we need to remove an electron. So let's remove it. We're going to remove one of those that are paired, and I mean you could either remove the 2px or the 2py. I removed the 2py. I need to make 4 bonds, so I need to promote again. One, 2, 3, 4, but I only have 1 lone pair, and I have 5 areas of density. 1, 2, 3, 4, 5. And let's see, we're going to have try to make this as realistic as I can. Of course, I know that I want the lone pair to be in the equatorial position and the trigonal bipyramidal family. And now I want the chlorines at the other 4 positions. Not going to put the lone pairs on chlorine, but rather emphasize the geometry. And if you've ever played on a playground, you should recognize that I've just drawn a seesaw. Here's the fulcrum of the seesaw. Here are the ends of the seesaw. This is seesaw shaped. ICl4 plus and ICl4 minus have very subtle differences. They're in entirely different geometric families. And that's because one results in 5 areas of electron density, while the other one results in 6 areas of electron density. So let's apply this. Let's just look at a couple other examples. Let's look at BCl3. Let's look at CF4. Let's look at XEF5. So if we look at BCl3, I will do a 4th one. XEF2. Once you get used to the what's going on here, all you got to do is do the ODEC for the central atom. So for boron, you've got 2s2, 2p1. But you know you're going to hybridize boron. Boron makes 3 bonds. Perfect. 1, 2, 3 areas of electron density. That's sp2 hybridization. That's trigonal planar. Game over. When you go to CF4, the ground state, you have 2s2, 2p2, but again, you're going to hybridize one of your 2s electrons to the 2pz. That's 4 areas of density, that's sp3, and it is tetrahedral. Now, xenon is a noble gas, but xenon, one element to the right of iodine, certainly has d orbitals that are available. So krypton and xenon, although they're noble gases, can actually make molecules in nature. So for XeF5, I'll promote once, twice, and 3 times. 1, 2, 3 times. And what I didn't show you is that you would have to lose one of those electrons, so it should be XeF5 plus. One of those goes away, and you have 1, 2, 3, 4, 5, 6 areas of density. So it's octahedral family where it's making 5 bonds. And what do you see when you go over the Mississippi River? The damn pyramid. That's exactly what you're going to have. Xe. Not going to show the lone pair at the bottom. In a different color. So I'm not showing the F's, but I'm going to show their overall shape. And if you're honest, that is the pyramid. So the last one, XeF2. This one's going to be pretty simple. I'm already going to show 1 electron hybridized. Five S. And I'm going to show the 5PZ, one of them promoted to the 5D. So here I see 2 electrons, but 1, 2, 3, 4, 5 areas of density. I've got 3 lone pairs, obviously. Lone pair, lone pair, lone pair. F and F. It is linear. So you can have a linear geometry if you're in the linear family, or if you are in the trigonal bipyramidal family, or if you are in the octahedral family. There is some redundancy in these geometries. So let's take a few moments to look through some past exams and see if we can find some molecular geometry questions and then go through this process to answer them with 100% accuracy. All right, so we're looking at full length one. We have 4 molecules, NO2, O3, ClO2, and H2S. Honestly, I would pick the easiest one to do, which is going to be H2S, because sulfur is going to look just like oxygen. What does H2O look like? It's bent, pick bent, Or if you want to see the full details, let's go back to the O deck. Sulfur, of course, 3s2 because it's a third row element. 3p4. We're not going to show any hybridization even though we could for this element because it's only making 2 bonds. So sulfur has 4 areas of density that's going to be tetrahedral. Lone pair, H and H, it is bent. Best answer is bent, which is choice B.